In section 4.5, we're going to prove triangles congruent by angle, side, angle, and angle, angle, side. And these are the last two shortcuts that we're going to have for proving triangles congruent. So let's test this first one. Is angle, side, angle a valid congruent shortcut? Notice I have two angles and the included side, meaning the side in between those two. I want to see if this works for a valid shortcut. Well, the only thing I can do is extend these rays, because I already have the angles defined by their size. So I'll just extend these. And this is kind of the easiest one to see, I think, because there's only one place where those sides meet up. I've formed the only triangle I could, and if I group these together, and group these, and I move it over, obviously the triangle that was actually formed is exactly the same. Angle, side, angle, with the side between the two angles that are congruent, is a valid congruence postulate. And notice that terminology there: if two angles and the included side, meaning the side in between, of one triangle are congruent to two angles and the included side of another triangle, then the triangles are congruent. So angle, side, angle being congruent is a valid shortcut to say the triangles themselves are congruent. Well, let's also test angle, angle, side. Notice here the side is not included. It is not between the two angles. So I have two angles, pairs congruent, and the side is not between them, so I have this side in red congruent. Now to form these triangles, this is the only side that has a definite ending point. It's the only segment. So I just have to go and line up these rays on bottom here until that red segment is right at the other edge. So that would be my triangle. Let's do the same here. I have to line up these rays because these angles need to be defined. That segment, though, has a specific ending, and it looks like right about there. I group those, and obviously the triangles are congruent when I have an angle, angle, then a side situation. So angle, angle, side, also a valid congruence postulate. Here, if two angles and the non-included side of one triangle are congruent to two angles and the non-included side of another, then the triangles are congruent. So if you have two angles, whether the side is in between those two, like angle, side, angle, or whether we have two angles and the side is not between those two angles, both are valid or working congruence shortcuts to show triangles are congruent. Little summary here, and a little explanation. We just saw that angle, side, angle, and angle, angle, side are valid shortcuts. Well, actually, they're really the same if you think about it, because once you know that two angles are congruent in two different triangles, or two angles here are congruent in two different triangles, you automatically know that third pair of angles is congruent. Remember, that's third angles theorem. You only need two angles congruent in two triangles because that third one has to be a certain angle measure. Now all the angles are congruent. So it's kind of neat that technically those are the same, because once you have angle, side, angle, you know that last angle pair would be congruent between the two triangles, which then makes it side, angle, angle, or angle, angle, side. Notice this one, if you write it the other way, it actually looks different. Every other one we've had has been symmetrical, so you can write this one either way. And I do want to summarize. We have now 4 shortcuts that prove that triangles are congruent. The very first shortcut we dealt with was side, side, side. If you have 3 sides congruent in 2 triangles, those triangles themselves are congruent. Then we talked about side, angle, side, where if you have 2 sides congruent and the angle that's included or between those two congruent in 2 triangles, then the triangles are congruent. And today we had 2 angles and a side, whether the side is between or included with those two, meaning angle, side, angle, or whether the side is not included, meaning angle, angle, then side. Those are all valid shortcuts to prove that triangles are congruent. Now, there are 2 other ways that you could arrange sides and angles in triangles that do not guarantee that they're congruent. They don't actually always work, so we can never use them. The first bad one we looked at dealt with all the angles being congruent. And the reason that one did not work was because you can make a triangle larger or smaller with the same angles. I mean, I could take this triangle right here and group that. I'm going to copy and paste it. Guess what? All the angles are congruent even if I stretch this. Look at that. All three angles are the same. But are the triangles the same? No. Okay, so angle, angle, angle does not always work. We cannot use it. The other one that does not always work that we can't use is the naughty word written backwards, SSA. And now the reason that doesn't work, side, side, then an angle. Okay, I need this side to be congruent, so I need to copy and paste that. Oh, actually, sorry, I'm going to change this because it has to be a side, side, and then an angle. Well, I'm going to take this side, copy and... Okay, I'm being really silly right now. Let's see. This side will be congruent, but I also need to make the angle right here congruent. And actually, this one could be any size, so I'm going to take a ray and go out that way. And now I'm going to copy and paste this. Okay, the reason why I did that is because this angle stays the same since I copy and pasted. This side is the same, but now it's side, side, then angle. So this angle has to come after this side. Now I'm going to kind of draw this freehand, but that last side could go this way, or it could flip out the other direction and still be the same. And I hope you agree that those two sides, even though I didn't copy and paste, are pretty much the same length. I formed two different triangles. Remember that SSA does not always work. The reason I summarized here is because today you're going to have to decide what shortcut's being used to prove the triangle's congruent, or are they trying to use one that doesn't always work. So let's take a look here. Can the triangles in each of these examples be proven congruent? How or why not? Alright, what about here? We got two triangles. One pair of sides is congruent. One pair of angles is congruent. But what else? Don't they share this side? So I can put two tick marks there. Is there a valid congruent shortcut that works? Well, it looks like we have an angle located right in between two sides. An angle located right in between two sides. Therefore, yes, these triangles are congruent by side, angle, side. The angle was included or between the two congruent sides. Oh, what about here? We have parallel lines marked. Parallel lines gives us information about angles. And actually, remember that Z shape that we get? Now these are, but this angle here would have to be congruent to this angle here because they are alternate interior angles. They're between the parallel lines on opposite sides of the transversal. They're congruent. These angles that I'm going to mark with two arcs are also congruent. Another pair of alternate interior angles between the parallel lines. Make that Z shape, opposite sides of transversal. And something else. What do you know about these angles? They're vertical angles, so they're also congruent. And I'll give them three arcs. Is that enough to say the triangles are congruent? I have angle, angle, angle. It looks like I have no sides. Does angle, angle, angle count as a valid congruent shortcut? No. One triangle could be larger, smaller. It is not a valid reason. Okay, it doesn't prove the triangles are congruent. It means they're similar. Remember, one can be larger or smaller and still the same angles. Alright, what about here? Two triangles. Looks like we have an angle congruent. We have a pair of sides congruent. And they share this side here, so I can actually do one tick mark since these had two already. Are these triangles congruent? I have two sides and an angle. The angle is not between the sides because if it was, it would be here. So it's side, side, and then an angle. Angle's not between the sides. Does that one work? Oh wait, side, side, angle was our other bad shortcut. It was the naughty word backwards. Is not a valid shortcut. So do I know for certain those triangles are congruent? No. It's not a valid reason. It doesn't always work. Alright. What about the two triangles shown here? I have one pair of angles congruent. I have another pair of angles congruent. Is there something else I can get from the picture? Well, actually, don't they share this side? So this side is congruent to itself. And now I have two angles and the side between them. two angles on the side between them, which would be angle, side, angle. Two angles, side between. And yes, it is a valid shortcut. So these triangles are congruent by angle, side, angle. So be able to use all of our good shortcuts today and identify when a non-valid shortcut is being used. Next cool thing we're talking about today is one more way to show or illustrate a proof. We've talked about two-column proofs, we've talked about paragraph proofs, and now our last type of proof is called a flow proof. It's a lot more visual. If you're somebody that likes diagrams and likes sort of those like thought webs, you're going to like this because you use arrows to show order. You're going to put each statement in a box with the reason below it. So instead of doing like statements, reasons, like a two-column, or writing it all out, you're doing a box. You put your statement in, give the reason right underneath. And I'm saying it can be vertical or horizontal. Vertical meaning like you can work your way down in the chart with the arrows, or horizontal meaning you can work your way across. And we'll do an example of each type of flow proof. We're using arrows to show or order boxes with statements and reasons. Alright, so I'm going to write a flowchart proof here. I'm given that AB and BC are, remember the symbol, perpendicular. AB and BC are perpendicular. I'm given that DC and BC are also perpendicular. And finally, I'm given that angle A is congruent to angle D. Alright, let's mark some things. What does it mean if AB and BC are perpendicular? Hopefully you're telling me that means they form a right angle. What does it mean if DC is perpendicular to BC? That they form a right angle as well. So I'll mark those. And finally, angle A was congruent to angle D. So I'll mark those. Alright, I'm trying to prove that triangle ABC, which is here, so maybe I'll highlight that. It looks like we're going to have some overlap. ABC, this would be that triangle there. Trying to show that that is congruent to triangle DCB. D to C to B. Okay, hopefully you just noticed something that they shared a side. We'll get to that in a little bit. Alright, I want a flowchart proof. Remember, we're using boxes to put our statements in. I have to start with what I was given. Alright, so in my first box, I'll put my first given, which is that line segment AB is perpendicular to line segment BC. And right underneath, I put the reason, which in this case, it was just given. And let's get another box here for my other given, that DC was perpendicular to BC. Also given, reason goes underneath. Now actually, I marked something additional because of these, so I need to create an arrow right below this. Now since I know that AB and BC were perpendicular, you were thinking this is a right angle, and I'm going to have to state that in a new box here. This is a new statement. Because AB is perpendicular to BC, I know that angle, well, at vertex B, so I'm going to have to name with 3 letters, angle ABC is a right angle. Angle ABC is a right angle. And how do I know that? Because of that symbol, perpendicular. Because perpendicular means that you are intersecting at a right angle. Therefore, I'm using the definition of that symbol or that word, perpendicular. And I'm going to have to do a similar thing over here. I know this is getting long now. But I had another pair of perpendicular lines. I also know that another angle is a right angle. Now DC, perpendicular to BC, gave me this angle as a right angle. That would be angle DCB. Is a right angle as well. And again, I know that from that symbol or the definition of perpendicular. Again, reason goes right underneath the statement. Oh boy, okay, so now there's actually more that I have to do with this. I said all of this to show that I have two right angles, but ultimately, if we want to prove triangles are congruent, I need to do a shortcut, meaning I need to show three things are congruent, so I actually have to say that these angles are congruent. I'm going to extend the page here to give myself some room. And I'm going to do an arrow from both of these together because both of these are leading me to a new statement, which is that these angles are congruent. Obviously, you have two right angles, and you know that right angles are congruent. So I'm going to say that that angle ABC, which is a right angle, is congruent to angle DCB, which is a right angle. The reason why, if you remember back to the last chapter, is right angles congruence theorem says that all right angles are congruent. Right angles congruence theorem. Whew, finally! Okay, I did all of this to show I have one pair of angles being congruent. I have two right angles. I'm going to go back up towards the top, and I'm going to write in our other given. Remember, we also have this given to us, that angle A is congruent to angle D. Reason underneath, it was given. Alright, automatically I had another pair of angles congruent. There's got to be something else. What else are we given in this situation? Or maybe not given, I guess, because we have to find something else. Right at the beginning I said, did you notice that these triangles share something? They share a side. They both have side BC. You can tell because it kind of turned green there. So I know that side BC in both triangles is congruent to itself. So I'm going to do another box up here. And I'm going to state that side BC is congruent to itself, side BC, and you should be getting familiar with this. What tells that something is congruent to itself is reflexive property. And here it's a property of congruency. And look at that, now we have a pair of sides being congruent. We should have enough info to say that these triangles are congruent because I'm going to draw from all three of these, here, here, and here. We have two angles in the side. Oh, I guess the question is, are the angles, or is the side between the angles, or is it the two angles then the side? Take a look at my yellow triangle ones. I have angle at D, I have the right angle at vertex C, then I have the side. Now the blue triangle, it's the same situation. The angle at A, the right angle at B, then the side. So this is an angle, angle, side, and that is going to be the reason for my very last box. Notice all three of these arrows come together to show this last statement that what I'm trying to prove, triangles ABC and DCB are congruent. And the reason? Angle, angle, side is a shortcut that allows me to say that. So I realize this flow proof is a lot of work just to show perpendicular lines mean right angles are congruent. The other two were fairly simple, but all three of these arrows come together, show triangles are congruent by angle, angle, side. That was kind of a vertical flow proof because I was moving down. Let's do one more flow proof. This time maybe we'll do horizontal, so we'll start over here and move to the right. Let's see. I am given that line segment CE is congruent to line segment CA. Maybe I'll mark these here. Okay, CE. I do have to be careful because that's the entire segment. It's congruent to line segment CA, and I have to be careful again because that's the entire segment. I'll kind of just go like this to indicate that it's the whole thing. I also know that angle E and angle A are congruent. Angle A congruent to angle E. I'm trying to prove triangle CAD is congruent to triangle CEB. Okay, because these overlap, I'm going to highlight again. Triangle CAD. C to A to D. So this is the triangle I'm looking at. And then triangle CEB. C to E to B. So this is my second triangle. Alrighty, let's start out with what we're given. do the easy part first, huh? I was given two. Oh, I'm sorry. I was going to do a horizontal proof. So we're working our way to the right. So I write my first given that line segment CE is congruent to line segment CA, that is given. And angle A is congruent to angle E, also given. Well, actually, this is kind of nice. Here's a pair of sides that are congruent right away. Here's a pair of angles that are congruent right away. There's got to be something else that I can get from the picture, from the diagram, because at this point, my given is exhausted, and there's nothing else marked. There's got to be something else I can observe. Now, normally we've been seeing sides shared. This is not a full side being shared. This is CB in the blue triangle, and this is only part of this side in the yellow. And same deal here, like this is part of the yellow triangle, this CD, but the blue side is all the way. It's not a side being shared in this case. Actually, there's an angle that's in both of these triangles. And you can kind of see it if you look here and notice which letter matches up is C, but wouldn't you say that angle C is in both triangles? It's in the blue triangle, angle C. It's in the yellow triangle, angle C is also there. So, in this case, for once it's an angle that is shared, that is in both triangles, part of both triangles, and I'm going to say that angle C, I can name with one letter because it's the only angle at that vertex, is congruent to itself, angle C. Again, what property says anything is congruent to itself? Reflexive property of congruency here. This is another angle pair. I have three pieces of info, so all three of these together should allow me to say in my last statement that the triangles are congruent. I'll list exactly what they wanted me to prove. That triangle CAD is congruent to triangle CEB. They wouldn't have given me something I can't prove, so this has to work. My question is it angle side or is it angle side angle? Because these might not be written in the correct order. How about we look at the yellow triangle here? Here's an angle that's marked. Remember, the side was the entire thing, and here's the other angle. So it looks like the two angles relative to the side is in between, because it was the whole thing between those two angles. Let's check the blue triangle. Once again, it looks like this side, which was the whole thing, is in between, or the included side for the two congruent angles. So the shortcut that works here is angle side angle, because that side was located in between the two congruent angles. Be careful with those overlapping. And this has been the first one where we saw a reflexive property using an angle, where an angle was in two triangles, which is kind of cool. So new type of proof today, a flow proof, and looking at all four congruent shortcuts that we're going to have for triangles: side, 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 angle, side, angle, and angle, side. And just be careful today that you don't let those maybe potential reasons fool you. Angle does not always work. Neither does side, angle.